Hello, this is Mr. Gilmore with the 1.5 Polygons lesson. This is actually a really important lesson today because we're going to be taking a look at what is a polygon and it's what its definition is, because what's going to follow in the chapters after this is we're going to be encountering actually a number of different polygons. We're going to see that we're going to encounter polygons that you may have heard of, such as triangles and quadrilaterals. We're going to be exploring those the rest of the year. So it's really important that we actually start to study what is a polygon, how do we name it, what are the things that we encounter when we talk about polygons. Let's jump right into the definition of polygon. This is possibly one of the longest definitions that we have of any term because polygons require really three things to happen. So each one of these sentences that we see in the first section here, that's the entire definition of polygon. So polygon requires three things to happen. The first is a polygon is composed of line segments. So that's the very first statement we see there. That's statement one. So it must be composed of line segments, which means there cannot be any bends or turns in our polygon. Now, the second statement, each intersects, we're talking about each, which means these segments, these line segments, each line segment intersects precisely two others, one at one of its endpoints and the other at the other. So that's our second statement that goes into the definition of polygon, that these line segments must intersect precisely two others. The last part of our definition, here's the last sentence. Adjacent segments are non-collinear. Essentially meaning if I were to draw a picture, we can't have a line segment do this and then a line segment look as if it's a straight line segment. That's not considered part of a polygon. We have to make sure that a line segment at least forms a non-straight angle there, so which means they cannot be on the same line or non-collinear. So all three of those statements combined, we have formed ourselves a polygon. Now, a little bit of jargon that goes along with polygons. We call the segments that form the polygon the sides. We also then take the intersection where those segments join, and we call those the vertex. If we have a plural of vertex, we call that the vertices. The vertices is plural of the word vertex. Here's a quick illustration of a polygon. We have it's actually a five-sided polygon here, and as you see, the side is pointing to the line segment, and the vertex is pointing to the point that joins the two segments together. Now let's kind of review, using the definition of polygon, whether or not we have polygons in the diagrams provided here. So there are 6 diagrams, and these are either examples or non-examples of polygons. So they could either be a polygon or they cannot be a polygon, and we're going to answer why they are not. Let's take a look at number 1. Is this a polygon, yes or no? Well, the correct answer is no. Now, a lot of times students would tell me why it's no. They would say, well, it's because it's still open. It needs to be closed. But look back at the definition. Did we use the vocabulary of the word open or closed? We did not. So that can't be your reasoning. We can't use vocabulary that we did not discuss. If I were to say no to this, which the correct answer is no, it's not a polygon, what would be my reasoning? Well, is it composed of only line segments? Yes. But do each line segment intersect precisely two others? Ah, that's where the answer is no. See, these two line segments here and here, well, they only intersect precisely one other line segment. They don't intersect another, which means that's where our definition fails. Let's take a look at number 2. Is that a polygon? Yes, it is. Okay, it satisfies the definition. Is it composed of solely line segments? Yep. Are each line segment connected to precisely two others? Yep. And are there any non-collinear? We're good on that. Yep, there's no non-collinear. Good, which means great, we've got ourselves a polygon. So 2 here is a yes. We've got ourselves a good polygon form there. Number 3, is that a polygon? No, it is not. Okay, why? Well, it fails right off the bat. Is it composed of solely line segments? Ooh, no, we've got a bend here. Look at this line. That's not a line segment, okay? That is a bend, all right, which means it's not composed of solely line segments. So no to number 3. Number 4, is this a polygon? The correct answer is no. Here's why, okay? Line segments must precisely intersect at their endpoints. But if you notice, that these two line segments here and here are intersecting other than at their endpoints. They're intersect on their interiors. That one's quite the most confusing amongst all of these 6 examples. That one is a no, and I do get some pushback on that. But because they intersect on their interiors rather than at their endpoints, we do not say that it is a polygon. Okay, so that is a definite no. Number 5, is this a polygon? That is a no as well. Here's why. Okay, it may not seem kind of obvious, but it's a little bit subtle there, which is if we take a look at this endpoint right there, every endpoint must intersect with precisely two or one other segment. But here, it's intersecting with 2 other segments, which means that's where it fails the definition. If each endpoint intersects at precisely 2, well, we actually have 3 intersections at that endpoint. Ooh, we can't have that. So because of this little extra kind of tail on the end of this polygon, that would make it then, or an end of this figure, that would not make it a polygon. Number 6, is this a polygon? And the answer there is no as well. All right, it feels like a polygon, it kind of looks like a polygon, but it's not. Again, we have some troubles here at these 2 vertices. Why? Each side or each segment must intersect with precisely 2 others. Ouch, it's intersecting with 3 others at that intersection point. So we've got to be extra careful. Okay, so you're going to be seeing questions like this on the worksheet tonight, where you're going to give it a diagram and you're going to answer yes or no. If you answer yes, move on. It's a polygon. It's a polygon, move on. But if you answer no, you got to explain why. My suggestion to you is look back at that definition of what the word polygon means. Now, we're going to look at what are called concave and convex polygons. In order to do that, we need a definition. Our definition we have here at hand is called a diagonal. A diagonal is a segment that joins 2 non-adjacent vertices. Now, this word adjacent really means next to or touching. So non-adjacent means 2 vertices that are not already touching. That diagonal is going to help us determine whether or not a polygon is convex or a polygon is concave. In order for a polygon to be convex, all the diagonals must pass through the interior of the polygon. But if there's at least one diagonal that passes on the exterior, then we call that the concave polygon. Let's take a look at an example of what a diagonal is, and then we'll take a look at an example of what a concave and convex polygon is. So here's an example of a diagonal. Here is a 5-sided polygon, and this dashed line is an example of a diagonal. It's connecting 2 non-adjacent vertices. These 2 vertices here would be considered adjacent because they're already connected. But if you take a look at this vertex and this vertex, they're not connected, which means if I were to draw this dashed line in, I would consider that a diagonal. Now, if we take a look at this example here, if I were to connect every single diagonal that's formed inside of here, notice that all the diagonals are on interior, which means we call this a convex polygon. Here's another illustration. This would be the same diagram we just saw previously, but this would be a convex because, again, if I were to draw in all of my diagonals here, they are all interior. So we find ourselves convex. However, in the second diagram here, it is concave. I can connect these 2. That's definitely interior. But these 2 vertices here, those are not adjacent. So if I connect them, look how that diagonal is on the outside of my polygon, which means that is considered a concave polygon. We will work with both convex and concave. I will say that percentage-wise, we work with a little bit more convex than we will see with concave. Okay, so either way, just keep in mind, concave, we find all the diagonals on the inside. Convex, we find all the diagonals inside, and concave, we find at least one to be on the outside. How do we name a polygon? Well, we already give names to points, right? A point is named using a capital letter. Well, as it turns out, the vertices of our polygon are points used to create the polygon. So if those points already have a name to them, the capital letter, let's use the points or the vertices that make our polygon to help name it. So here's the process of naming a polygon. We start by picking a vertex, any vertex on our polygon. So if it's a 5-sided polygon, 10-sided polygon, whichever one it is, you pick a vertex. From that vertex, you then choose a direction. Are we going to go clockwise around this polygon, or are we going to travel counterclockwise? Either direction is fine. But what you do is as you move from the vertex you've chosen around the polygon, you're going to write the vertices that you encounter. So we're going to see a quick example here of how do we name a polygon. So down below, we have a 4-sided polygon. If you notice each of the vertices, we have point W, point X, point Y, and point Z. So how can I name this polygon in a valid sense? Well, what I could do, let's say I start by choosing point W. I can either then choose to move clockwise or counterclockwise, or really, I choose a direction. Am I going to travel toward X first, or am I going to travel towards Z? Let's say I travel towards X first. So I travel towards X, then I can travel towards Y, and then I travel towards Z. And what I'm really doing there is I'm strategically naming my polygon. So the polygon I just named is W, X, Y, Z. That's its name. That's a valid name for this polygon. What are some other valid names? What if I don't want to start with the vertex W? That's fine. Pick a different vertex. For the second example, let's say I pick the vertex Y. Now, with vertex Y, I have two choices. I could travel towards Z or travel towards X. So, let's say I travel towards X. Then I take X towards W, and then W towards Z. That is another valid name, Y, X, W, Z. What we have to avoid is traveling along the diagonal. I don't want to travel. I can only travel along the sides. I cannot travel along diagonals. So for example, this one here, this XZWY, let's watch what happens. XZ, oh, wait a minute. XZ goes, it goes along a diagonal. No way, I can't name my polygon like that. XZWY, whoa, that is way wrong, right? I did travel along a side here, but I travel along another diagonal here. Yikes, cannot do that. All right, so what we have to be careful with is as we pick our direction, we stick with the adjacent vertices in this case, not trying to follow along a diagonal. Now, you'll notice this is a 4-sided, which means it required 4 letters. If it was, let's say, 5-sided, it would require 5 letters. If it were 10-sided, it would require 10 letters. Now, as we then move out into other types of polygons, we actually do have categorizations by the number of sides. And you guys will recognize these words. For example, we start with what's the smallest polygon in our set here. The smallest polygon that we can ever create is using 3 sides. We call that a triangle. And I'm sure you guys recognize that. A 4-sided polygon we call a quadrilateral. A 5-sided we see pentagon. A 6-sided is hexagon. So let me go back here. That's the 3-sided. This is the 4-sided. There's the 5-sided. A 6-sided is a hexagon. This may be a new one, a heptagon to you. That's a 7-sided polygon. Then you have an octagon. That's 8-sided. You have the nonagon. That's 9-sided. You have a decagon. That's 10-sided. Now, if I were to test you and I use any of these words, I'd be expecting that you know what these words mean. Up to decagon. Anywhere past decagon, I'll provide you with what the name of that polygon is. So I wouldn't ever go above a decagon, okay? Down below, though, you're going to see, well, is there another way we could name polygons? Well, technically, yes. See, you can actually name an n-sided polygon with the name n-gon. What that means is, if it's a 3-sided polygon, you could technically call it a 3-gon. If it's a 4-sided polygon, you could call it a 4-gon. If it's a 5-sided polygon, you call it a 5-gon. If it's a 100-sided polygon, so 100 sides, you can call that, let's fix that, you can call that a 100-gon. Yeah, because really past decagon, I know some of the names past decagon, but I don't know what a 39-sided polygon is. No way. So what would I call a 39-sided polygon? I'd call it a 39-gon. If I were to see a 141-sided polygon, I don't know what the name of that one is, but I would call it 141-gon. And very rarely, very, very rarely will we go anywhere past a decagon. There are some cases where I go to a 12-sided polygon, which is called a dodecagon, and we talk a little bit about dodecagons. But Our primary focus throughout the year is actually right here with a triangle. We're going to study triangles quite a bit in the following chapters to come. Now, a few definitions is what's going to then conclude our lesson today. Let's finish off with the definition of equilateral. The definition of equilateral is if we call a polygon equilateral, it simply means that all sides are equal. Now, be careful. Equilateral says all sides are equal. It mentions nothing about the angles of the polygon being equal. However, we do have another definition of describing a polygon in which all the angles are equal. We call that an equiangular polygon. It's actually kind of a fun word to say. If you want to take a moment just to say it to yourself, equiangular. Yeah, equiangular polygons are polygons in which all the angles are equal. So our example below, we see that all the angles have the same measure. Don't but in reality, don't also assume that all the sides are equal, because equiangular just says it has equal angles. But there are polygons in which there are both equilateral and equiangular. We have a name for that. We call them regular polygons. Regular. A regular polygon is both equilateral and equiangular, meaning all sides are equal, all angles are equal. If we encounter a polygon that is not regular, we have a name for that as well. It's just simply irregular. Irregular is probably the easiest definition in this entire year. Irregular just simply means not regular. Okay, not regular. Yeah, super easy. So down below we have an example of a regular hexagon. It's a six-sided polygon. Regular hexagon. All six sides are equal. All six angles are equal. We make good use of those hash marks. But then to the right of that, we have a diagram of an irregular polygon. I can already tell that these two sides given here are not the same length, so it's not equilateral, which then means it cannot be regular. So we call that an irregular polygon. Well, that is it to today's lesson. We've encountered a couple different definitions. We saw how a polygon works. We saw how to name a polygon. If you do have any questions with this lesson, please don't hesitate to get in contact with me. Email me, contact me in any way, shape, or form. I will get back with you. So with that, be good and do good.